wave optics. Now this chapter of wave optics basically deals with the wave theory of light, as you all know. Now this chapter is basically more interesting than the last chapter, because as you all know that the last chapter was more like a mathematical topic, but this is actually a conceptual topic. Moreover, there are some physical phenomena which you can relate with this wave theory of light. For example, if you have a compact disc, if you have a CD, you see, for example, that this is a CD I have on my hand. If I keep rotating the CD, I see that for different angles, the color appearing on the top of the CD is different. For example, sometimes I see a yellow green pattern, sometimes I see a red green yellow pattern, and the pattern keeps changing as I keep changing my angle of viewing. Okay, now this is a very common physical phenomena which we observe, and this can be explained with the help of wave theory of light. Another example could be, you all might have seen a peacock, the national bird of India. You see that the feathers of a peacock, the peacock basically looks very beautiful because it has different colors which keeps changing as you keep looking at the peacock from different angles. Sometimes you see a dark green pattern, sometimes you see a dark blue pattern. Now people have a misconception that this pattern which we see on the body of the peacock is because of some pigment present on the surface of or the skin of the peacock, but it actually is a very beautiful example of wave theory of light. Another example could be butterfly. A butterfly looks very nice, it looks very beautiful. Again, the different colors on the feathers of a butterfly can be explained with the help of wave theory of light. So you see that there are three examples which can be proved with the wave theory of light. So these are some examples which I guess are good enough to raise your interest in this topic. Now let's begin with this topic. The wave theory of light, as you all know, was first proposed by Christian Huygens, and what he said was that light is actually a wave, and the wavelength of the wave is very less compared to the dimensions of the object which we measure. Okay, now using this concept he proved the laws of reflection, diffraction, and what he said was that when light travels from a rarer to a denser medium, the speed of the light decreases. Speed decreases, or speed of light in denser medium is less than speed in the rarer medium. Now this was in contradiction with the particle theory of light. The particle theory of light at that time proposed that when light moves from a rarer to denser medium, the speed of the light increases. So this was in contradiction with the particle theory of light, and that's why this was not accepted at that time. Moreover, there was inclination of the people towards following Newton's theories, and Newton had proposed the particle theory. So the people were reluctant to follow the wave theory of light. Now after this, some years later, Thomas Young, you all know, performed the Young's double slit experiment, and he observed some repeated patterns, alternate patterns of dark and bright fringes, and that phenomena couldn't be explained by the particle theory of light, and so this was the time when the wave theory of light came into existence. After that, a lot of experiments were performed on diffraction, polarization, and finally it was accepted, okay, that light also has wave theory. Now then, after that, as I had discussed in my last chapter, that then there was photoelectric effect which couldn't be explained by wave theory, and for which we had to consider the particle theory of light, and finally it was decided that okay, fine, light is both a wave and a particle, it has dual nature depending on the situation. Now when after this interference, diffraction and polarization experiments, there was a people had a very big question that they believed that waves need a medium to propagate, and they found it disturbing that light was traveling in vacuum, because vacuum doesn't have a medium. So how come if light is a wave, light travels in vacuum? It was then when Maxwell proposed his electromagnetic theory, and he said that light is an electromagnetic wave, and electromagnetic waves doesn't require medium to propagate. So this was about the brief history about the wave theory of light. So now let's begin with what Christian Huygens had proposed, and let's prove the laws of refraction and reflection with his principle. Before we do that, let's understand a concept known as what is a wavefront. Let's say that you drop a stone into a pond. What happens? As soon as you drop the stone into the pond, you see that there are circular ripples formed around the place where you had dropped the stone, like this. So if I take a snapshot of the whole thing, the top view of that looks like this, right? So this is the top view. Now what can I say? I can say that these points or the particles in this circle all oscillate in phase. Now if all these particles are in maxima, all these particles in this circle will reach its zero at the same time, and it will reach its negative at the same time. Similar things happens with particle in this circle. Similarly, a particle in this circle could be at its minimum point, and after some time it may have a maxima. So all the particles in a particular circle oscillate in synchronization with each other, or I can say that they oscillate in phase. They oscillate in phase. So these surface or these circles of constant phase is known as a wavefront. It's basically a surface of constant phase. Okay. So if you have a, let's say if you have a point source and it emits waves in all directions, then what are my wavefronts? If I say that this point source emits waves in all directions in the space, then what is my wavefront? Clearly my wavefronts are spheres now, because if I take any particle in a particular sphere enclosing this point, then those particles will be oscillating in phase. So my wavefronts are in the form of spheres, right? Because see, waves will be emitted in all directions like this, onto the surface, into the surface. So this particle, this particle, this particle all will oscillate in phase. Similarly, this distance is r. Similarly, a particular distance r from this point on the top will also oscillate in the same phase. So I'll get a spherical wavefront. Now, and the spherical wavefront will be increasing in diameter as I move outward from the center. Now as I move too much outward from the center, let's say my point source is here which emits waves, and I am moving here. Now if I take a small cross section, what I'll see that this small section will look like a straight plane surface, and I can say that here I can approximate here that the wavefronts are plane for this portion. Similarly, for this portion I can say that this wavefront is a plane wavefront. So if I take the radius to be infinity, what happens? The wavefronts actually become plane wavefronts because the radius becomes too large. Now, so that was all about wavefronts. Now let's see what Christian Huygens proposed. Let's see what he proposed. He said that if I know the shape of the wavefront at any particular time, let's say t is equal to 0, if I know the shape of the wavefront, Then I can determine the shape of the wavefront at any particular time, let's say tau, if I know the velocity of the wave or the velocity of the wavefront. If I know the velocity and if I know the shape of the wavefront at any particular time t, then I'll be able to find the shape of the wavefront at any particular time tau. And how we can do that, he said that each point on a wavefront is a source of secondary wavelets or secondary wavefronts. So what he said was that, let's say if I have this wavefront at time t is equal to 0, then I can determine the shape of the wavefront at time t equal to tau. And how we can do that is that he said that each point on the wavefront, for example each point on this wavefront, this point, this point, this one, 1, 2, 3, 4, 5, each point is a source of secondary waves. So waves will be emanating from here, from 2, from 3, from 4, from 5. Now to find the shape of the wavefront at any particular time tau, we need to basically do a geometric construction. So what we do is that, let's say that this is my shape of the wavefront at time t is equal to 0. Now this is a source of wave. So if I take time tau and I'll draw, let's say I cut an arc of radius v tau, because this distance is v tau. Similarly, from here I can cut a wave of arc of v tau. Here I can cut an arc of v tau. Now if I join the common arc to all these arcs, then I get the shape of the wavefront after a particular time tau. Remember, here I know the direction of the wavefront, that the wavefront is traveling in this direction. If I don't know the direction of the wavefront, then I can get two cases, wavefront like this and a wavefront in this direction also. Okay, fine. So this was what Christian Huygens said, and this is known as the Huygens principle.